So the May equation so far is a periodic, that is to say irregular. It is certainly bounded. It is certainly deterministic. Right? I mean, xn plus 1 equals f of xn. How much more deterministic can you get? And that means, in particular, no outside noise. Nothing is injected into the system. So these are three of the defining conditions of chaos. What about sensitive dependence? The answer is shown here. This is two tracings, one of them from x0 equals 0.2 and the other one from x0 equals 0.201. And what you see should be looking fairly familiar by now. The green and the orange tracing start out exactly overplotting each other because those values are very, very close. As you go forward in time, there's a little bit of separation between the green and the orange. And by n equals 20 or 30, there is complete separation of the green and the orange. And if you know the green, what can you predict about the orange? Nothing. Because after 30 or 40 iterates of f, the green and the orange are completely decorrelated, and the green is high and the orange is low, or vice versa. So we do indeed have extreme sensitivity to initial conditions. This makes for a sort of a fun example. I like to give the assignment to students, and the assignment is I pick a number at random. If today was February 5th, I would say let x equal 0.25. And we will now take this as our initial condition, and I'm going to give you a little homework assignment, which is x0 equals 0.25, xn plus 1 equals 4 times xn times 1 minus xn. Now compute x50. And by the way, to avoid a degenerate situation here, let's pretend it's February 4th. And we're going to have x0 equals 0.24, because there are certain points that end up stuck at 0, and I believe 2.25 is one of them. Let's take 0.24. So I like to tease students and say, okay, A plus in this class, if you answer the following simple question: x0 equals 0.24, xn plus 1 equals 4 times xn times 1 minus xn. Tell me x50, and I will give you an A plus in the class. You don't even have to take the final. So everybody goes, is this a trick question? And the answer is, alas, yes, it is a trick question. And that is revealed the following day when the students show up with their answers. I want the number that is x50. So you call upon the first person and you say, Karen, what did you get for x50? And she says 0.2378 something. That shouldn't, actually, I shouldn't pick something close to 0.24. You might be misled. Let's say she says 0.3378. Then I call upon Robert and I say, Robert, what did you get for x50? And he says 0.9124. And then I call on Kayla and I said, Kayla, what do you get for x50? And she says 0.1366. And we all look at each other and we say, what the heck is going on here? I asked you a simple question. There's no calculus, there's no limits, there's no approximations, there's no nothing. Here's x0. I asked you for x50. I got 10 different answers that are wildly different to that question. So who is right? Which one of these people is right? And the answer is none of them is right. They're all wrong. There is a correct answer, but you can't find it. And the reason why you can't find it is contained in this function itself and in the property of sensitive dependence. So everybody starts out x0 equals 0.24. As you calculate x1, it's going to be 4 times 0.24 times 1 minus 0.24. But if you multiply this out for easier calculation, it's 4xn minus 4xn squared. So you calculate this in 2 steps. You calculate 4xn, and then you square xn, and then you subtract 4xn squared from 4xn. This squaring has a consequence. The square of a 2 decimal place number is a 4 decimal place number. I don't want to do it in front of you. But it's longer. The square of 0.3 is 0.09, 2 decimal places. The square of 0.09 is 0.0081, it's 4 or 5 decimal places, depending upon your choices. In other words, every time you square a number less than 1 that's written as a decimal, you get a longer number. And as a matter of fact, the length of this number is going to grow as roughly 2 to the n. So when you get down to calculating x50, how long is x50? The answer is it's roughly 2 to the 50th digits long. That's approximately 10 to the 13th digits long. We saw the same thing in the Hastings system. So you would have to, and I can tell the class, I know that none of your answers is correct, because none of you wheeled in a large refrigerator-sized memory storage unit, which is what you would have needed to store the correct answer. 10 trillion decimal places. This is one heck of a long number and could not be stored in any computer that you or I own. So what do our computers do? Well, they round off. What is round off? Round off is after 16 digits, it stops and it truncates. Okay, that means that your computer has just introduced an error into the calculation, and the error is every number to the right of that round off cutoff point. Once you have done that, you have introduced a small difference between this number and the correct number. So you think, well, 16-digit accuracy, that's good. But the answer is no, it isn't good, because in about 4 or 5 iterates, by the time you do an X5 or X7, you've already used up the 16 digits of accuracy. So you've now introduced error. That error is going to grow exponentially, and so it's going to produce wildly different answers from people using different programs, different languages, different brands of computer, are all going to introduce round-off errors slightly differently, and they're all going to give you wildly different answers to the question, what is X50? So the bottom line here is, once again, prediction in detail. The question, what is X50, is unanswerable. Prediction in detail is impossible.